Hi, my name is Hermano, and this is my Physics2211 Lab 4 video report on oscillations. A quick overview is the introduction, fundamental principles, the code, the results, the errors, and the discussion. And the purpose of this lab was to analyze the motion of a two-dimensional spring mass system where the mass oscillates while swinging in an arc, and then compare the tracker data to a computational glow script model. And to do this, I use tracker to record the data, experiment, X and Y position data, and I use glow script to model the system computationally. The main physics principle in this lab we use were Hooke's law, uh, the momentum principle, gravity, and the energy principle. And the main result was that the computational model of the experimental data showed similar oscillatory motion, and the total energy remained nearly constant, which means the energy principle was approximately satisfied. And for the system and surroundings, the system was the oscillating mass attached to the spring, and the surroundings were Earth, the spring, and the fixed support, and the surroundings interact with the mass mainly through the gravitational force and the spring force. And the main fundamental principle used in this lab was Newton's second law, or the momentum principle, which says that the net force equals the rate of change of momentum over time. In this system, the net force is the sum of the spring force and gravitational force. Gravity pulls downward, and the spring force acts along the spring. The other main principle was the energy principle in the computational model. The total energy of the system is the sum of the kinetic energy, gravitational potential energy, and spring potential energy. So for this lab, total energy was calculated using K plus U sub plus or plus G, or U sub G plus U sub S. And for the initial conditions of the model, the mass was 0.402 kilograms. The initial position came directly from the first tracker data point, and the initial velocity was estimated from the first two tracker points. I also used G equals 9.8 meters per second squared, a spring constant of 6.872 newtons per meter, and a relaxed spring length of 0.1261 meters. The position came from the experiment data. The constant was found from the oscillating period, and the relaxed spring length was determined from the equilibrium conditions. I also included a slide showing the tracker video data, since that was the source of the observed X and Y position values used in the comparison. And for the computational model, I first defined the spring geometry and the system energies. I used the vector L to describe the spring's length and direction, and I used S to measure how much the spring was stretched relative to its relaxed length. Then I calculated the kinetic energy, gravitational potential energy, and the spring potential energy and add them together to get the total system energy. And then after that, I created the motion prediction loop. And in this loop, the code calculates the gravitational and spring forces, adds them to get the net force, updates the velocity and position at each time step, updates the spring length and direction, and then calculates the changes in kinetic, gravitational, spring, and total energy. And for the results, the computational and observed motion were reasonably similar. In both the x position and y position graphs, the model and the experiment curves follow the same overall oscillation pattern. The periods were very close, which shows that the model captured the motion reasonably well. And there were still small differences in amplitude and phase between computational observed data, especially as time went on, but the overall agreement was still good. And some possible sources of error in this lab came from tracker or measurement error, model assumptions, and numerical approximation. Small inaccuracies in tracker points and placements and calibration could shift measured X and Y position data. The computational model also assumes an ideal spring mass system, so real effects like air resistance and non-ideal spring behavior were not fully included. And then finally, a repeating time step updates estimated initial conditions can introduce small phase and amplitude differences over time. And to answer the first, what does it mean question? Yes, the energy principle was approximately satisfied. The kinetic, gravitational, and spring energies all changed throughout the motion, which means energy was being transferred between forms. However, the total energy stayed very close to zero over the entire time interval. That shows that the total energy of the model remained nearly constant. And for the second, what does it mean question, I estimated that oscillation periods separately from the tracker data in the X and Y directions. And for the X position data, the average oscillation period over 5 cycles was about 1.65 seconds. And for the Y position data, the average oscillation period for over 5 cycles was about 1.52 seconds. The difference between the two estimates were about 0.13 seconds. The two values are still reasonably close, which suggests that the X and Y data describes the same overall oscillatory motion. The small difference is likely due to tracker measurements, uncertainty, graph reading error, and slightly non-ideal behaviors in the real system. And overall, this showed how the momentum principle, spring forces, gravity, and energy conservation can be used in a computational model to predict oscillatory motion and compare that prediction to real experimental data. Thank you for watching.